Have you ever thought about how you'd actually tell the full story of a journey? I don't mean just where it started and where it ended, but every single second in between? Well, today, we're going to decode that secret language, and all it takes are a few simple lines on a graph.
Take a look at this. This jet car hit an absolutely mind-blowing 763 miles per hour. But how would you describe that whole trip? Not just the top speed, but every moment of acceleration, every single foot it traveled. That's the story we're learning how to read today.
You know, it's funny because motion is something we experience every day, right? But it can be super counterintuitive. Our gut feelings about how things should move are often, well, just plain wrong when you look at the actual physics. And that's a huge hurdle for anyone trying to learn this stuff.
And it's not just you. Research shows these misconceptions are incredibly common. Have you ever mixed up velocity and acceleration? Or just felt like those physics equations were totally disconnected from the real world? These are the classic stumbling blocks we're about to completely demolish.
But what if I told you there was a way to just bypass our faulty intuition? A kind of visual secret code that lets you see the story of motion, making all these abstract ideas crystal clear. Well, there is, and it's all about graphs.
So, let's start with the basic tool itself.
We all remember y equals mx plus b from math class, right? But in physics, this isn't just a formula. Oh no, it's a storyteller. That m, the slope, that tells you the rate of change. And b, the intercept, that's your starting point. This is the basic grammar of the language we're learning today.
All right, let's look at our first clue.
Here is our jet car again. Now this graph plots its position on the vertical y-axis against time on the horizontal x-axis. And you can see it's a straight line. That tells us something is happening at a constant rate. But what is it?
The key, the secret to unlocking this whole thing, is hidden right there in the slope of the line. As soon as we figure out what that slope means, we've cracked the first part of the code.
Okay, quick refresher. Slope is just rise over run. So on this graph, the rise is the change in position, right? And the run is the change in time. So the slope is the change in position divided by the change in time. Does that ring a bell?
It should, because that is the literal definition of velocity. So here it is, the first huge takeaway. The slope of a position-time graph is the object's velocity. A really steep slope, high velocity. A flat, horizontal slope, that's zero velocity. The object is just sitting still.
Okay, but this is where it gets really interesting. What happens when the line isn't straight? A curve, like this one, tells us the story is changing. Since the slope is changing at every point, that means the velocity must be changing. This car is speeding up. So how in the world do we find the velocity at one specific instant on a curve? Easy. We just draw a straight line that barely kisses the curve at that single point. That's called a tangent line. The slope of that line gives us the instantaneous velocity. It's like a snapshot of how fast the car is going at that exact moment in time.
Now, let's get to the most powerful tool in our entire kit.
Check this out. See the relationship here? The position graph on the left is a curve, which we now know means the velocity is changing. Well, if we actually graph the value of the slope at every single point on that curve, we get the straight line on the velocity graph on the right. See how the curve starts out kind of flat and gets steeper? Well, the velocity graph starts low and increases steadily. We've literally just translated one graph into another.
And this one graph, it gives us everything. Seriously, it holds two incredibly powerful secrets. Rule number 1, the slope of this line tells you the acceleration. And rule number 2, the area underneath the line tells you the displacement, how far the object actually went.
Let's break that first rule down. Slope is rise over run, right? So here, that's the change in velocity divided by the change in time. And guess what? That is the definition of acceleration. So if the velocity is changing really fast, you get a steep slope, which means high acceleration. If the velocity isn't changing at all, you get a flat line, zero acceleration. Make sense? And that second rule is all about the area. If you literally calculate the area of the shape between the velocity line and the time axis at the bottom, the number you get is the total change in position, or the displacement. So this one graph tells you velocity, acceleration, and displacement. It is the complete story of the object's motion.
And this is the aha moment. This is where you realize that all those abstract physics equations you had to memorize aren't random at all. They come directly from these pictures.
We can actually build one of the most famous equations in physics right from this graph. We know acceleration, a, is the slope, and that's the change in velocity over time. If we call our final velocity v and our starting or initial velocity u, then the change is just v minus u. Do a tiny bit of algebra and boom, you get v equals u plus at. It's not magic, it's just the equation for this straight line.
And we can do the exact same thing with the area. To find the displacement, we just need to find the total area under this line. And we can easily split this shape into two much simpler ones, a rectangle on the bottom and a triangle sitting on top.
So let's do the math. The area of the rectangle is its base, which is time t, times its height, which is the initial velocity u, so that's ut. Simple. The area of the triangle is 1/2 its base times its height. The height here is the change in velocity, v minus u. But wait, remember from the last slide we figured out that v minus u is the same thing as at. So the triangle's area is 1/2 times t times at, which is 1/2 at squared. Now, just add them together. The total displacement, s, is ut plus 1/2 at squared. Another famous equation born right out of the shapes on this graph.
Okay, let's put this all together into your new physics toolkit.
This one slide right here is your cheat sheet. This is everything. For a position time graph, the slope is velocity. For a velocity time graph, the slope is acceleration, and the area under it is displacement. You can even take it one step further. For an acceleration time graph, the area tells you the change in velocity. See? It's all connected in this beautiful, logical way.
So we started with a 763 mile-per-hour jet car and discovered that its entire, complex story could be told with just a few lines on a page. So it makes you wonder, now that you can read the story of motion in a simple line, what other complex things out there could be decoded if we just knew how to look at the right graph?